Okay, so many thanks for the introduction. I have two preliminary remarks. First, I'm not used to give course with the slides. Usually I'm writing on the board, and especially for 5 hours, so I hope you will excuse me. And point two is that the audience is very diverse, not only geographically. It's already late in Wuhan, and it's too early in Santiago de Chile, but in terms of background. So I hope that each of you will nevertheless understand a piece of what I'm saying and learn something. Okay, so this is the dynamic and games, and this is abstract. So in general, game theory studies interaction between agents. Okay, it can specific aims, be they rational actor, genes, or computer. And the purpose of this course is to provide the main mathematical concept and tools used in game theory, and especially to focus on the connection with learning and convex optimization. So the first part will be upon the basic notion, value, equilibria, correlated equilibria, and we'll give several proof of the min-max theorem and speak about black hole approachability. The second part will introduce no-grade properties, and then I will describe later on the menu of next week. Okay. So let us start now. Part A is today, and A1 is this morning. Okay, so this section relies very much on the books that I wrote with Jean-François Martin and Saint-Shmuel Zamir on one hand, and with Rider Laraki and Jérôme Renaud on the other. Okay, so this is the content of this morning lecture, introduction to strategic games, 5 proofs of the min-max theorem, and then part on equilibria. So these are the notation that I will use. The strategic game is defined by a set of players, capital I. Each player has a set of strategies that is denoted by SI, and there's a mapping G from the product of the SI to RI. So the interpretation is GI of S is a payoff of player I when the profile S is played. There is this usual notation of S as SI, S minus I, where S minus I is the vector of choice of the other player than I. I will use this notation given a set K. Delta of K will be either the simplex when the set is finite, or the set of Borel probability measure on K when K is a compact metric. When you have a game G, it could be useful to use the mixed extension. So mixed extension means that you look at the set of mixed strategy, which is a simplex over or delta of SI. And then there is a multilinear extension of the payoff defined on S to sigma, assuming a Fubini's theorem. So the interest of mixed extension of a game is that you convexify the set of strategies and you convexify the payoff function while keeping the topological property. So if the set of strategies is compact, the set of mixed strategy will still be compact. If the function is the payoff function is continuous, then the mixed extension will still be continuous. In addition, you have geometrical properties. Now some definition. So the main concept will be the best reply correspondence. So the epsilon best reply correspondence for player I is a function defined on S minus I, which is it's the set of small si that give the best payoff up to epsilon. Okay, so it associates to every profile of the opponent the set of epsilon best reply of a player. I will denote by capital BR the global best reply correspondence, okay, where each component is BRI. The extension to the mixed extension of the game is straightforward. If you have any clarifying question, please let me know. Equilibrium, a Nash equilibrium introduced by Nash in his studies in the 50s, is a profile of strategy where no player can gain by changing his strategy. Okay. So first we look only at unilateral deviation, and at strictly profitable unilateral deviation. So an equilibrium is a profile where there is no unilateral strictly profitable deviation. More generally, you can define epsilon equilibria, which means that if you move, you will not gain by more than epsilon. Okay, so S is an equilibrium if and only if F is a fixed point of the best reply correspondence. Okay, so this is the main use of the best reply correspondence. An equilibrium is strict if it's the only best reply to itself. Alternatively, we can say that a profile T eliminates a profile S if there is a player I for which Ti is better than Si facing S minus I. Okay, so you look at a profile S and then there is an alternative profile T. If one player will prefer the component Ti to Si, then T eliminates S. So if we denote by E of T the set of profiles that are not eliminated, an equilibrium is a point in the intersection. Okay. So this formulation is the spirit of an equilibrium being a rational rule of behavior, meaning that it's a profile that is not eliminated by any other profile. In the framework of two-person zero-sum game, we have the notion of value. So two-person zero-sum game is a game where there are two players, okay? And given a function from the product S cross T to R, so when there are two players, I denote S1 by S and S2 by T. The payoff of player one is F and payoff of player two is minus F. So the sum of the payoff is zero, the interest of the player opposite. And in this framework, one introduced the following quantity. V lower bar is the sum F, V upper bar is the F sup. So think of player one who is maximizing. Okay, if he chooses a strategy S, the worst for him is the infimum with respect to T of F of ST. So the best for him in this case is the supremum with respect to S of the infimum with respect to T. So it's V lower bar. Okay, so that's what I wrote there. V lower bar is the largest amount that player one can guarantee. And we said that the strategy of player one is epsilon optimal if it guarantees V lower bar up to epsilon. The game has a value if sup F equals F sup. The link between value and equilibria is as follows. If the game has a value and you have strategy of both players that are epsilon optimal, then they form a two epsilon equilibrium. In particular, if epsilon is zero, this gives a saddle point of the function f. Note nevertheless that there are games that has value, but no zero optimal strategy. We'll discuss later on the connection between value and equilibrium. Min-max theorem. So I first consider the finite case. The set of pure strategy or action or moves are finite. So S is denoted by I and T is denoted by J. The payoff of the game G is represented in this case by a matrix because it's a function defined on a product of finite set. And an element X of delta of I is a row matrix. So it's a mixed strategy of player I. It's a probability distribution on a finite set. An element Y in delta of J is a probability distribution of J. It's a mixed strategy of player 2. And the payoff is given by f of xy. So it's its expectation. It's a mixed extension, and it takes the form of the bilinear form xay. So I don't put transpose, okay? Some people put the transpose for x. Here it's just the bilinear form xfy. So it's a summation of xi, aij, yj. And the fundamental theorem of von Neumann that goes back to 28 is as follows. You take a real I cross J matrix, then there is a triple of strategy of player one, X star, mixed strategy of player one, mixed strategy of player two, Y, and a number V such that if player one use X star, then he will get at least V, whatever being the Y used by player two. And if player 2 use Y star, then the payoff will be at most V for every strategy of player 1. Okay? So it means that the mixed extension of a matrix game has a value. I will say that any finite zero-sum game has a value in mixed strategy, and both players have optimal strategy. This was for a matrix with value in the real, but there is the same theorem in ordered field. The real number in the theorem is uniquely determined and is the value of the matrix. So V is the max min and the min max. It's also denoted by val of A. So val is an operator on the matrix, okay, which is positively homogeneous. So if you multiply the matrix by a positive constant, the value is multiplied by the constant. It's increasing, monotonic, and it's non-expansive, meaning that if you take two matrices, then the difference in absolute value of the values is less than the infinite norm of A minus B. And this is a general property that extends to any zero-sum game. Min-max theorem, general case. So in this framework, S and T are subset of Hausdorff topological vector space. And the main theorem is due to Maurice Sion. It's 58. So you have a game, zero-sum game, that satisfies the following. Both sets of strategy are convex. One of the two is compact. And for every T, the payoff of player 1 is quasi-concave and upper semi-continuous with respect to S. It means that the upper level of F of T being given are closed and convex set. And similarly, for every S in capital S, F of S is quasi-convex and lower semi-continuous in T. Then the game has a value, so super equals un sup, and the player that has a compact set of strategy has an optimal strategy. The proof uses the following intersection lemma, which is due to Berge, and says the following. You have a finite collection of non-empty compact convex subsets. You assume two things. First, that the union of all these sets is convex. Then that if you drop one set, the intersection of the remaining is non-empty. The consequence is that the full intersection is non-empty. It's clear if you have two sets, okay, you assume that they are non-empty. If the union is convex, then the intersection has to be non-empty, okay? Because otherwise you use the unbalanced separation theorem. In fact, the proof of this lemma is by induction on N and use only the unbalanced strict separation theorem of compact and closed convex set. I will not going to prove this, it's quite elementary. Reference is MSZ is Mertens, Sorin, Zamir. LRS is Laraki, Renaud, Sorin. Everything is fine? Okay, so now I'm going to prove Sion's theorem using the intersection lemma. I assume that the set is compact, S is compact, and the proof is by contradiction, like all the proof in the compact case. I assume that the game has no value. It means that there is a real number V between sup and sup. Okay. We first reduce the case where the problem to the case where S and T are polytopes. Okay. So for each T in T, I look at the set S sub T, which is the set S where G of ST is strictly below V. So because of this, for every S, there is a T such that G of ST is smaller than B. So it means that the family ST, when T varies in capital T, is an open covering of S. So there is a finite subset such that the set ST where T belongs to T0 are sufficient to cover S. So by looking at T hat, which is the convex hull of T0, it's a convex and compact set, we have still the contradiction that the max inf is smaller than V and smaller than the inf sup, replacing T by T hat. Okay. But now both set S and T hat are compact and convex. So I will do the same now using the set S to cover the compact space T hat. So finally, I get the following. There is two finite subsets of S and T, such that denoting by S hat the convex hull of this finite subset, S0, for every S in S hat, there is a T such that G of ST is smaller than V. And for every T in T hat, there exists S in S0 such that G of ST is greater than V. I can assume that this family ST0 is minimal, otherwise I just drop 1 point. Now, using this property, I see that for every S, the set AS of T, such that G of ST is smaller or equal to V, this is non-empty and convex and compact. So convex and compact, it's because of property of G. Remember that G was quasi-convex and lower semi-continuous, and the other property is because of this. Okay. Now, the intersection is empty because of this property. Okay, for every T, there is a S such that G of ST is greater than V. And by minimality of the set S0, if I drop one element in the set F0, the intersection is non-empty. So using the intersection lemma, this implies that the union of the S is not convex. Remember that the intersection lemma, there were two hypotheses. First, the union was convex. Two, the intersection of all set except one was non-empty. And the conclusion was the intersection of all was non-empty. In our case, we have the intersection of all are empty, and the intersection of all except one is non-empty. So it implies that the union is not convex. Since the set T hat and S hat are convex, it means that the union doesn't cover T hat. So there is a point T star in T hat minus the union of the pairs. Okay. So it means that you are in T hat and you are in none of the ES. So it means that G of S and T star is strictly greater than V for all S in S0. I use now the quasi-concavity of the function G of T star as a function of S to prove that this inequality holds for every S in S star. Okay? Because it's strictly greater at the extreme point, so it's greater or equal to V plus epsilon at the extreme point, and then I use quasi-concavity. Similarly, there exists S star in S hat such that G of S star T is greater, smaller than V. And then if you consider G of S star T star, it's at the same time greater than V, strictly, and smaller than V, strictly. This is the contradiction. And this is the end of the proof of Sylvain's theorem. So basically the idea is, if the game has no value, then there is a smaller game construct in the convex hull of finitely many points that has no value. And for this game, I use the intersection lemma. So basically, I use the intersection lemma in finite dimensional space to get a contradiction. Okay? A third theorem is in the compact case, the mixed extension. So take a zero-sum game, G, and assume that S and T are compact. For each T, F is upper semi-continuous in S. For each S is lower semi-continuous in T. I assume that F is bounded and measurable with respect to the product Borel field. Then I use the mixed extension. This is what I was saying. So the mixed extension allows to convexify the set and keeping the topological property. So if I look at the delta of S, delta of T, it's convex and compact. And now the function was upper semi-continuous. The extension will still be upper semi-continuous, but it will be linear. So in particular, it will be quasi-concave or quasi-convex. Okay. And so the mixed extension has a value. And in addition, each player has a mixed optimal strategy. And for each epsilon, an optimal strategy with finite support. I recall this much, so these results are from the 50s, okay? There was a much earlier result by Jean Ville, who was a student of Borel, and he proved the min-max value on the square. And it was the first proof of the min-max using Hahn-Banach theorem. The proof by von Neumann in 28 was using a fixed point. Okay? So Ville proved that if you have a jointly continuous function on the square, then the mixed extension has a value. For more results on the min-max theorem, I refer to MSG section 1.1 and LRS section chapter 3. Okay, now min-max principle. So this is an example due to Oman and Maschler and shows the difference between an analysis in terms of max-min, min-max optimal strategy or of equilibrium. Okay, so it's very simple. It's two-person game, non-zero sum. So the component on the left is the payoff of player one, and on the right of player two. So if player one plays top and player two plays left, the payoff of player one is 2, and the payoff of player two is 0. Okay, and similarly. So it's very close to a constant sum or zero sum game. If you replace 2 by 1, it's a zero sum game, but it's not non-zero sum. If you look only at the payoff of player one and you consider this as a zero sum game, so it's 2, 0, 0, 1. It's a zero sum game. The value is 2/3, and an optimal strategy of player one is to play top with probability 1/3 and bottom with probability 2/3. Similarly, if you look only at the payoff of player two, it's 0, 1, 1, 0, and you consider a zero sum game, the value is 1/2, and optimal strategy of player two is 1/2 on left, 1/2 of right. On the other hand, the game has a single equilibria, which is given by x star, y star. X star is 1/2, 1/2. It's equalizing the payoff of player two, and y star is 1/3, 2/3, equalizing the payoff of player one. And the equilibrium payoff is 2/3, 1/3. So you see that the equilibrium payoff is equal to the value for each player. So for player one, the equilibrium payoff, which is its value, 2/3, but the equilibrium strategy does not guarantee the value. And the max-min strategy guarantees the value, but if you look at the both min-max strategy of both players, it's not an equilibrium. Okay? So if you add this strategy to the matrix, you get the following game. Okay, so this is the initial game, left, right, top, bottom. Here I add the equilibrium strategy. Here I add the optimal strategy. Okay, and so similarly for player one. So you see the equilibrium strategy gives a constant payoff to player two. Okay, the equilibrium strategy of player one gives a constant payoff to player two. Okay, the equilibrium strategy of player two gives a constant payoff to player one. The optimal strategy of player one gives him a constant payoff. The optimal strategy of player two gives him, player two, a constant payoff. The equilibrium strategy of player one doesn't guarantee 2/3, because if he plays the equilibrium strategy and player two plays right, he gets 1/2. Similarly, if player two plays the equilibrium strategy, it doesn't guarantee 1/2. But the optimal strategy are not in equilibria. If player two is playing the optimal strategy, player one should play top. It's the best reply and get 1. And if player one is playing his optimal strategy, player two should play left and get 2/3. Okay? So just to summarize, equilibria strategy in this framework are equalizing the payoff of your opponent. Max-min strategy are equalizing your payoff. Okay, so the next 5 sections will provide proof of the min-max theorem in the finite case. Okay? Obviously, these are consequences of Sion's theorem, but remember that Sion was not constructive. This will be more or less constructive. Okay? So the first proof of the minimax arrays is using ordinary differential equation, and it was provided by Brown and von Neumann in the 50s. And we first prove that if you have an antisymmetric matrix, so B is minus transpose of B, it has a value. Obviously, if it has a value, the value is 0 by symmetry. I denote by X the simplex on I. And to prove that the game is a value is to prove that there is some X such that Bx, which is a vector, has all components less than 0. I introduce K of X, which is the positive part of this quantity. So EI is the vector where the only component, the only non-zero component is i's component, which is 1. Okay. And plus mean that take the positive part. K bar is the sum. And I consider the dynamical system on X, which is defined by this equation. So this is the time derivative of the I component of X, okay, at time t, which is Kf of t minus this. Okay. So if you take the sum of the xi dot t, you get the sum of the ki. Here you have the sum of the xi, which is 1, which since you are in the simplex, so you get only k bar, and k bar is the sum here. So it means that the sum of the derivative is 0, so you keep the simplex. So this is a dynamical system on the simplex. If I look, introduce V to be the sum of this quantity square, and the rest point of this dynamical system is X of B, which is V minus 1 of 0. It means that each Ki is 0. In fact, if you have a rest point, the time derivative is 0. It means that for every I, Ki equals Xi K bar. And if you replace here, this gives that V of X is K bar XBX, and XBX is 0 because the matrix is antisymmetric. Now, this will be a Lyapunov function. Take the derivative of V of xt. You get twice K of xt, and then the derivative of X dot, which is given by this. This is the expression because X dot is this. Okay, and what you obtain is this term will cancel because B is antisymmetric, and you get minus 2 K bar V of t. Remember that K bar is positive, so V is strictly decreasing on the complement of X of B, and compactness implies that the accumulation points of xt are in xb. Okay, because V is decreasing as long as is strictly decreasing as long as it is positive. So the accumulation point will have V equals 0. Okay, so it implies by compactness that the accumulation point are in V minus 1 of 0, which is X of B. So X of B is non-empty, and the matrix has a value. Now, to deduce the min-max theorem, we have to deduce from A that any matrix has a value. And to prove this, it's enough to prove that you can reduce the case to antisymmetric case. So first, we can assume that the matrix has all entry positive, otherwise I add a positive constant to each of them. And there are two ways of transforming a game into an antisymmetric game. The first one was defined by Gale, Tune, and Tucker in the 50s. And starting with the matrix A, you introduce the antisymmetrics B, matrix B of this form. So you have 0 here, 0 as the size of the transpose of A, then A minus 1. So this is a one-dimensional column. This is a one-dimensional line. And this is the size of matrix A, and this is the transpose of A. Okay. And if so, this matrix is anti-symmetric, so it has a value and optimal strategy. And if you look at an optimal strategy, X, Y, T for player 1 in this game, so X corresponds to the component on the first block, Y the component in the second block, and T is a scalar, you show easily that X of and Y normalized are optimal strategy for both players in the game A. Basically, it's as if player one was playing as player one in the game A and as player two in the game minus the transpose of A. An alternative proof, which was already in the paper by Brown and van Neumann, is to consider the larger matrix A cross G cross time A cross G. So the set of strategy of player one is A cross G. And in this case, you play explicitly, simultaneously in both games as maximizing and minimizing. So I is the strategies that you play in the game A as player one if you maximize, and J in the game if you minimize. So the total payoff is given by this. Okay. So clearly, this game C is antisymmetric. It has a value which is 0. Okay. And obviously, you deduce from an optimal strategy of player one in the game C, an optimal strategy in each of the games for the optimizer in game A and for the minimizer in game B. In game A. Okay, so this was the first proof of the min-max theorem. A second proof is using the replicator dynamics, and I follow a proof of Joseph Hofbauer. So we introduced the replicator dynamic that was defined by Taylor and Jonker, which is defined by the following equation, starting from a point at the interior of the simplex. Okay. So x dot, so this is always the time derivative is EIA y star. So this is a payoff if you play I facing yt minus the average. Okay, and the same for player two, except it's minus the payoff. Okay, and it's plus here. Okay, so this defines trajectory in the simplex. Okay, because if you take the sum here, you get xia xt, and when you take this term, you have the sum of the xit. Since you are in the simplex, sum of xit is 1. So the derivative of the sum is 0. So the simplex is preserved, and if the initial point has a positive component of y, then it will still be positive for everything. I introduce the time average x bar t. Okay, so it's a time average of the component. Okay, so it's a vector in the simplex, which is the time average of trajectory here. I use this definition writing this way. So x dot it over xit is equal to this. And then I integrate here. So what I get is 1 over t, the log of xit minus the log of xi0 equals aix, so the integral, the average of y, minus the average of the integral of the payoff. Okay? I'm just integrating from 0 to t the previous equation. I take now a sequence on which, a subsequence on which the average of the strategy, the average of the strategy of player one, of player two, and of the average payoff converge. So this will be a mixed strategy of player one, a mixed strategy of player two, and this is a number. Then using the previous equation here, so this will converge to AXY, this will converge to W, and this, this term here is obviously negative, okay? Because it's a log of a point and the component is in 0, 1. Okay, so what I get is W is smaller than AY A star and greater than AI A Y star and less than X star for LYJ. So this implies that the game has a value, which is W, because by playing X star, you get W for every J. And similarly, by playing Y star, you are less than W for every I. And X star, Y star are optimal strategy. Okay? So in fact, the proof shows more. It means that any accumulation point of the average trajectory of the replicator dynamics belongs to the set of optimal strategy of player one, and the average payoff, okay, on the given this trajectory converges to the value. Okay, the third proof will be a minimax theorem via an unilateral process. So it will be a kind of constructive proof. The previous one were in continuous time using dynamical system and differential equation. The next two will be in discrete time. Okay, and I will use this process again in this afternoon and in the next in the talk next week. Okay, so there is a preliminary result, which is as follows. You take a non-empty closed convex subset of Rk, and using the Euclidean structure on Rk. So pi c is the closest, pi c of z is the closest point, a closest point to c, okay, which is also the projection. Okay. And I consider a bounded sequence, bounded by M, and I denote by z bar the Cesaro mean of the sequence between stage 1 and M. I will say that Vn is a Blackwell C sequence. So it means it's a Blackwell sequence adapted to C if you have this property. So you start from Dn plus 1, and you project on, so it means that starting from the average Cn, you project on C, and you have this scalar product, which is negative. Okay, so we'll see this when dealing with approachability later on. And the idea is, okay, starting from the average, you project on the C, and the scalar product between the point and its projection and the new point is negative. Okay. So we'll see this property when we discuss approachability. And the lemma is that if you have a Blackwell sequence, then the distance of the average to the set converges to 0. And it's just a geometrical property in Hilbert space, okay? But here it's finite dimensional. So I will denote by UN the projection over C of the average. Okay, so you have an arbitrary sequence of points in Rk. I denote by Zn bar the average. I project the average. This is UN. I look at Dn plus 1 square, which is the distance of the average up to stage n plus 1. So in particular, since UN is in the set C, because it was a projection of the previous average, the distance here is smaller than this. Here I split, introducing the n bar. Okay. And then I decompose Zn plus 1 minus Zn using the fact that this is Zn plus 1 is 1 over n plus 1, Zn plus 1 was Zn bar. Okay. This is the classical difference of Cesaro average. And then I have Zn bar minus Un. Okay. Again, I decompose introducing Un here. So I have Zn plus 1 minus Un plus Un minus Zn bar. So I get this point plus. Okay. Now I use the hypothesis that I had before, which said that Dn plus 1 minus the projection, scalar Dn bar minus the projection is negative. to obtain finally that dn plus 1 square is smaller than 1 minus 2 over n plus 1 dn squared. This was a term, plus this term here that comes from the point here, dn plus 1 minus dn. Okay? I use now the fact that the sequence is bounded, okay, to deduce that dn plus 1 is smaller than this quantity here. Okay? And now by induction, this implies that dn is smaller than 2m over square root of. Okay? So this sequence converges to 0. The consequence of this lemma will be the min-max theorem. So I take a matrix A and I assume that the min-max is 0. Okay? So it means that the minimum on y, maximum on x, x a y is 0. So it means that player 1 cannot get more than 0. Okay, player 2 can force player 1 not to get more than. And to prove the min-max theorem, it's just enough to show that V lower bar is greater than 0. Okay. The player 1. So if player 2 can prevent player 1 to get 0, and this is the best he can do, then player 1 can get 0. And we'll construct by induction an optimal strategy. And the way it works is as follows. We will construct a sequence Zn. And then we'll apply to this sequence the previous lemma. So the first term in the sequence, so its sequence will be in R capital J, so it's indexed by the set of strategy of player 2. Okay, so it's a vector. It's a vector corresponding to the row matrix. Okay, so the first Z1 is any row of the matrix, and inductively I define Zn plus 1 as follows. First, I look at the average up to stage n, so it's Zn bar. I take the positive component in each coordinate. If all components are positive, I take Zn plus 1 any row. Otherwise, I consider the components that are okay, so this I consider Zn plus minus Z bar n plus minus Z bar n. Okay, this difference. Okay. So this is positive. Okay, always. If the component is positive, this is 0. If the component is negative, this is 0, and minus the n is positive. Okay, so this is a vector with positive component, and I divided by n to normalize and to get the point in the simplex. Since the min-max is 0, facing this considered as a mixed strategy of player 2, there is a way for player 1 to get 0. Okay, because the min-max is 0. It means that the best that player 2 can force player 1 is 0. Okay, it means that given any strategy of player 2, player 1 can get 0. So there is a pure strategy of player 1 that gives him, facing yn, a positive component. So I define Zn plus 1, so this is the new element of my sequence, as the line of the matrix corresponding to this choice yn plus 1. Okay? So I just repeat, at stage n, you look at the average Zn bar, you look at the positive part, and you look at the component, in fact, that have negative payoff. Okay? And you normalize it, and you play a best reply to this normalized component, which correspond to. So in fact, it's basically from the point of player 1, you look at the worst path behavior of player 2, and you play a best reply to this worst path behavior. Okay. So by construction, in plus 1a is cn plus 1, and yn was this vector normalized. For any vector, the positive part time the positive part minus the initial vector is 0 because it's a decomposition. So you get that dn plus 1 minus dn bar plus scalar, this is negative null, okay, because this is positive, okay, and the other is negative. I change the sign here, okay. Now consider C as being the set, the positive orthant. Okay, so the set of vector in Rg where all the components are positive. Okay. So the n plus is in fact, when you have a vector in Rj, the positive component is the projection on the positive orthant. Okay, so this is the projection of the positive orthant, and this is the projection of the positive orthant. So this equation 4 exactly means that this sequence Dn plus 1 is a Blackwell sequence for the set C, which is the positive orthant. Dn plus 1 minus the projection of the average times the average minus its projection is negative. Okay? Maybe I can come back to this condition here, Blackwell sequence, Dn plus 1 minus the projection of the average, scalar the average minus the projection. Okay, so this is exactly this equation 4 here. Okay, so this proves that the n is a Blackwell sequence. The n bar, remember that the n corresponds to a line. So when I take the average of the line, it's like taking xn bar A, where xn bar corresponds to the average. So xn bar is a mixed strategy of player one. Any accumulation point of this sequence xn bar now will satisfy x at A is in C, because this is a Blackwell sequence and the n bar converges to C. But to say that x at A is in C, it means that all the components are positive. So x at y is positive for every y. This means that player one can guarantee 0. So the lower value is greater than 0. Okay, so we prove that if the max min is 0, then the min max is greater than 0. And this is the min max theorem. Okay. Fine. Okay, so the next proof of the min-max theorem will be using a fictitious play. So I start with the real matrix A, and fictitious play was a process introduced by Brown in 51, the same Brown that wrote this paper with von Neumann, the first proof that I described using the differential equation. So now we consider two players. The previous proof was unilateral. It's a single player who is playing basically by himself, choosing every day a line of the matrix and looking at the worst behavior from his point of view of his opponent and playing a best reply to this fictitious opponent. Okay, so if this fictitious opponent cannot force you to get a payoff less than 0, then you can by yourself get a payoff of 0. This was the spirit of the previous unilateral proof. This proof here will use both players. So the game is repeated. Okay. In a repeated zero-sum game, it's clear that if at each time you play a best reply to what the other was doing, then you may get a cycle, and it's not very interesting. So the fundamental idea of Brown was to use memory. So the two players are playing in a repeated way the matrix. At each stage, each player is aware of the previous action of his opponent, but he looks at the average behavior of his opponent. Okay? And then he plays an action which is the best reply not to the previous action of his opponent, but to the previous average of his opponent. Okay, and this is basically the idea, fundamental idea of Brown. So explicitly, we start with any move, and at each stage n, you define xn to be the average of the move of player one, which is obviously distribution on pure move, so it's a point in the simplex. And similarly, yn is the empirical distribution of move of player two up to stage n. And then we say that a sequence with value is a realization of a fictitious play process for the matrix A if at each stage n, yn plus 1 is the best reply to yn. So yn plus 1 belongs to br1 of yn. It's the best reply from the point of view of player 1 to the average behavior of player 2. It means that AYAXN is better than this. Okay. And similarly, Jn plus 1 is the best reply of player 2 to the average behavior of player 1 in the past. Okay? And the main property are given by this. So the theorem is proved by Robinson. So Julia Robinson was a student of Brown, and at some point she was the president of the American Mathematical Society. And this was part of her PhD. And she proved the following. If you look at the realization of a fictitious play process, then the distance from yn xn to the set of optimal strategy goes to 0. Remember that xn and yn are the empirical distribution of moves of both players. So explicitly, it means that for every epsilon, there exists a large number of stages, such that if you look at some stage after n, okay, then you are close to the set of optimal strategy, meaning that xn ay is greater than the value up to some epsilon, and ymx is smaller than the value up to some epsilon. Okay, so you are in the neighborhood of the set of optimal strategy. Okay, the distance to the set of optimal strategy goes to 0. It doesn't mean that the trajectory converge, okay, but the distance to the set of optimal strategy goes to 0. And moreover, the average payoff and the trajectory converge to the value. Okay, so we'll give a hint of the proof of the theorem by looking at the continuous time analog. This is expressed in discrete time. The process was expressed in discrete time. The proof is simpler in continuous time. This is in the spirit of what I'm going to do this afternoon and next week. Okay, so I take as variable the empirical frequency xn and yn. So the discrete dynamic is like this. Xn plus 1 is the move at stage n plus 1 plus the average move up to stage n. And the move at stage n plus 1 is the best reply to the average distribution of move of your opponent. So you have this equation. Xn plus 1 minus xn belongs to 1 over n plus 1 br1 of yn minus xn. Okay, this is yn plus 1. Okay, and this is a discrete differential inclusion. Okay, the difference in the average move of player 1 is a point in this set. Okay, so the corresponding system in continuous time, okay, will be x dot. This is the time derivative 1 over t br1 of. Okay, this is now a differential inclusion, which defines with a similar condition for player 2 what is called the continuous fictitious play process, CFP. Okay. Now, we write the payoff as f of xy. Okay, so it's and I will introduce the two quantity. L of y is the maximum, so it's the best you can do against y. M of x is the best player 2 can do against f. And the duality gap is defined as the difference here. Okay. And it's easy to see that a pair of strategy will define optimal strategy in the set A if and only if the duality gap is 0. Okay. It's also saying that the min max min. Okay. So this will be the quantity that we will use to show the convergence property. Okay, so the proposition just follows. It was done in the finite case by Christopher Harris, and we did it with Joseph Bauer for continuous convex concave function. So you look at the continuous fictitious process, then the duality gap converges to zero at a speed which is big O of 1 over t. Okay, so we take the time change. I go back to this continuous fictitious play process. I will drop this term by making a time change. Okay, and then I get this autonomous differential inclusion. X dot belongs to BR1 of yt minus xt, and y dot, and this is called the best replied dynamics. Okay, BR dynamics, and was introduced by Gilboa and Matsui in 91. Okay, and I will basically work with this one. So I take a solution of this equation, and I denote by Wt the evaluation of the duality gap on the trajectory. Okay, so remember that on the trajectory you have x dot which belongs to this. Okay, so it means that x dot plus xt is in BR1. So if I denote by alpha t this quantity, I have alpha t in BR1 of yt, and similarly beta t is in the set of best reply to xt. Remember that by definition, L here is given by the max, so it means that X prime belongs to the set of best reply to Y. Okay, so it means that L of Yt is realized at alpha t. So in particular, if you take the derivative of L of Yt, is the derivative of this function, okay, and then you use the envelope theorem to see that the first term collapses because this function is maximal in alpha t realize the maximum of this function. Okay, so it remains only the second term. Sorry. Okay, and the second term is just f of alpha t y dot because the function is f is linear because it's x, y, y, so it's linear with the second variable. So this shows that the time derivative of the duality gap is given by this. This is f of alpha t y dot minus f of x dot beta t. Okay, and you lose again bilinearity. Alpha is x plus x dot. Beta is y plus y dot. Okay, so there's the term that disappeared, and you replace now again y dot by beta plus. So beta is y dot plus yt. Okay, so we have the same term here. You get this quantity, and this is simply m of xt minus yt, so it's minus w. So you have exponential convergence to zero. Okay, so the duality gap converge to zero at exponential speed in the best reply dynamics. So without the change time, you have a speed of convergence in 1 over t in the original problem before the time change. Okay. So since the duality gap converges to zero, it implies by compactness that the set of xtyt converge to optimal strategy. In particular, the set of optimal strategy is non-empty. And this is the new proof of the min-max theorem. Okay. So in fact, the result is stronger. It shows that the set of optimal strategy is a global attractor for the best reply dynamics, okay, which implies the convergence of this discrete time version. So it implies the convergence of the fictitious play process, which is part one of the theorem of Robinson. Okay. So in fact, there were two parts in what I did. One was to prove the min-max theorem, namely that accumulation point of the trajectory of the best reply dynamics were optimal strategy, and also that the property of the continuous time process implies property of the discrete time process. So this kind of result will be described next week in a part on stochastic approximation. There's an alternative proof using differential equation by Lehrer and myself. Okay. It remains to prove the last part of the Robinson proposition, namely that the payoff on the trajectory of a discrete fictitious play process converge to the value. And it's very simple but very nice. You look at the set of realized payoff. Okay. So at stage P, so we are in discrete time, player one plays YP, player two plays JP. What can you say? YP is the best reply to what player one, player two was playing in the past. JP is a best reply of player two to what player one was doing in the past. So what can you say about this term? Okay, well, what is nice is you will write UIM to be what player two got in the past. Okay, so you decompose this term by saying that you look at what you got, what GP was getting against all the payoff in the past minus of all the payoff up to stage P minus one. So basically you have this. Okay. This can be written this way. And now you use the fictitious property, which says that what you are using against the past is the best. Okay, so YP plus one is the best you could get, okay, because it's the sum of the payoff. Okay, UIM is the payoff that you get if you use Y against the previous move of your opponent up to stage M. Okay, so since everything is linear, if you take the average here, it's the same that taking the average inside here, and Y is the best reply to the average. So you get this property here. It means that all these terms here are negative. So it implies that the limb sup of this quantity is bounded by the limb sup of the maximum of this average here. And this is smaller than the value, since this is given by f of yn, and yn is an optimal strategy, well, or close to an optimal strategy of player two by the previous result. Okay, so it implies that this average payoff is smaller than the value for the limb sup, but you have the dual result saying that the limaf will be greater. So it implies that the average payoff on the trajectories converge to the value. And this is not a consequence of part one. Part one shows that on the trajectory, the accumulation point will be optimal strategy. Part two says that on the trajectory, the average payoff will converge to the value. These are independent. In general, convergence of the average marginal trajectory on move does not imply any property on the average payoff. Okay, if you look at this game, optimal strategy are 1/2, 1/2, but you can realize 1/2, 1/2 by, for example, alternating on the second diagonal. So you play top left, bottom right, top left, bottom right, top left. So the average behavior of each player will be 1/2, 1/2, and the payoff will be 1 on this trajectory. And you could also alternate between top right and bottom left. And the marginal distribution for each player will be 1/2, 1/2, so it will correspond to optimal strategies, but the payoff on the trajectory will be -1. Okay, so the two parts in the theorem of Robinson are independent. Okay, so this is the last proof. Okay, I can. Stéphane?
Oui, yes.
Should we take the break now?
As you like, yes, if you like.
Okay. Maybe it's a good time, okay? So that I will also get some feedback. Okay, so if you have any comment, please write on the chat. I will look at the chat during the break. We'll have a break now for 10 minutes.
10 minutes, yes, 10 minutes. So,
Okay.
up together 24. Thank you very much, Sylvain.
Okay, so let us have a 10-minute break right now. Okay, and if you have comments, please write on the chat. And thanks.
This conference will now be recorded.
Voilà. So, Sylvain, it's to you.
Okay, so just one point concerning the previous proof with fictitious play. So I introduced the fictitious play process for a 2% zero-sum game. Obviously, it can be defined in a general framework, and I will study this afternoon. Now I give the last proof, which is not in the same spirit as the previous one. The previous one were more or less constructive. The two first were constructing a process in continuous time. The two last were constructing a process in discrete time. This proof now that I describe is by induction on the size of the matrix, and it's not constructive, but it's very elementary and very nice. In fact, if you look at the original proof of John Robinson of the fictitious play property, her original proof, it's using basically the same idea than the proof by Loomis, okay? And by induction on the size of the matrix. And it's very elementary and I like it very much, okay? So Loomis was also a student of von Neumann, and it goes back to 46. You have two matrices, and you assume the same size, and the matrices B has all strictly positive entries. Then there exists, again, X, which is a mixed strategy of player 1, so it's a point in the simplex, Y, a mixed strategy of player 2, and a real number such that XA is greater than VXB. So here XA is a vector, okay? It's a product by the vector X by the matrix, so it's a vector. V is a number, XB is a vector which has the same size than the vector XA. So this is a vectorial inequality and similarities, okay? I could have put EJ yes and EJ there and say that it's true for every J, okay? Now, okay, obviously, if you take the matrix B to be just one everywhere, then XB will be the sum of the component of X, and it's one because you are in the simplex. So you have XA greater than V, AY smaller than V, you have a von Neumann theorem, okay? But if you look at, if you think of this as a bilinear form, so you multiply here by y prime, okay? And then since B is strictly positive, you have ratio. So you can consider this as a min-max theorem for rational fraction, okay? Bilinear or fraction of bilinear form, okay? And this was used by von Neumann in his proof of the growth model. So the proof of Loomis is by induction on the dimension. Obviously, if you have one matrix, it's true, and you assume that the result is true for, so the induction is on the sum of the size of line and column, okay? So assume that the result is true for m plus n minus 1. You look at the largest number, such that this is true. Okay, so you look at the largest lambda such that there exists S in delta of I, such that you have this property, and the minimum number for player 2. Obviously, if Borg quantity are the same, then this will be the V here, and you have the result. Otherwise, the best that player 1 can do will be lambda 0, and the worst it will be mu 0, and you have always this. So this is the assumption, like in the min-max theorem, that the game has no value. Denote by S0 and T0 optimal strategy, so meaning that these are points that realize the maxima, and then you have this equality. Okay, and you cannot have equality on all components because by multiplying here by T0 and there by S0, you will have equality between lambda 0 and mu 0. Okay, remember that B is strictly positive, so S0B, BT0 will be a strictly positive number. Okay, and so you can assume that there is a component, a point G bar in J, such that against G bar, you have a strict inequality. Okay, so basically you have an optimal strategy of player 1. So it means that you get always lambda 0, but if player 2 is using J bar, you have more. Okay, you cannot have equality everywhere, and you have inequality everywhere. So if you don't have equality, you have a strict equality somewhere. Okay. So now you look at the game where player 2 cannot use this move. Okay, and then you use your induction hypothesis. So I introduce V prime, S prime, and T primes that are associated to the submatrices of A and B obtained by dropping the column J bar. Okay. And obviously, you have this property because S prime is optimal for player 1 in the new game. Now, in the new game, the value, so by induction, the new game, the M plus N is decreased by 1 because you drop either a column or a line. Okay. So by induction, this game has a value. And the value of the new game is greater than the value of the old game. Why? Because player 2 has less strategy. So you take in the max mean, the mean on a smaller set. Okay. So this implies that V prime is greater than mu 0, and mu 0 was supposed to be greater than lambda 0. Now I consider a strategy S, this should be S equals, which is a convex combination of S prime. So S prime is optimal in the small game, and S0 was optimal in the large game. Okay, and alpha is a coefficient in 0, 1. And the claim is that for alpha small enough, you will have that this strategy applied to A minus lambda 0 B J is strictly positive for every J. Why is this true? For G bar, it's true. Why? Because here, you remember in the previous slide, here you have a strict inequality. Okay? So it means that for alpha small enough, you have still a strict inequality. Okay, and for the other, you have S prime against the G that are not G bar. You are in the previous, you have in smaller game G prime, and in the small game you get V prime, and V prime is greater or equal than mu 0, which is strictly greater than lambda 0. So you have a convex combination of something which is greater than 0 and something which is strictly greater than 0. So the convex combination, you are strictly positive. Okay? So it means that against every J, you have a strict inequality here. And this contradicts the definition of lambda 0 being the supremum of all real such that you can guarantee. Okay? So the spirit is the following, and Shapley was using this sentence to explain it. If the min-max theorem was wrong for a matrix, it should already be wrong for a submatrix, and then you go by induction. Okay? So this is the story. And in the proof of Robinson, it's a bit like this. You look on the trajectory of fictitious play. If you use all your moves, and it's easy to see that if you use all your moves, then you will have equality and there will be a value. So it means that on a large block, you are not using one of your moves, but then you are using the fictitious process in a smaller submatrix. Okay, and by induction, in this smaller submatrix, fictitious play process converge. So this is basically the idea of the proof of Robinson. Here, just a fancy application of this result here. You take now A to be the identity. Okay, so B is any strictly positive matrix, and A is the identity. So you have A, which is greater than VB, and Y, which is smaller than VB. Okay, so you get that there is an eigenvector associated to a positive eigenvalue with positive components. So this is pair of Frobenius. That's all for zero-sum games. Okay, so just to summarize, I introduced the game, equilibria, value. I proved the min-max theorem in the compact case. Okay, this was Sion's theorem. Okay, which is not constructive, and then I gave four elementary proof of the min-max theorem, 2 in continuous time, 2 in discrete time, and 1 by induction on the size of the matrix. Now I go to non-zero-sum games and equilibria. Okay, so general result, which is the existence of equilibrium in the compact case. So the main result, it's Nash, so it's the second version of Nash theorem, and there are versions due to Glicksberg and Kieffer. So there are two versions, one in pure, one in second in mixed. First one. So if SI, so you have a finite set of players, each player has a set of strategy SI. Assume that SI is compact convex, topological vector space, and the payoff function of each player I is continuous on S and quasi-concave with respect to SI. Okay, so this is the main difference with the zero-sum case. You have joint continuity here. In the zero-sum case, remember the payoff was upper semi-continuous in the component X and lower mid-continuous in Y. Here you assume that you have continuity. You need continuity or almost joint continuity with respect to what the other are doing. Okay, and then there are equilibria. The set of equilibria is compact. So the mixed version, if SI is compact and the payoff function is continuous, then the mixed extension of the game has an equilibrium. Proof, so I prove one. So by continuity and compactness, for each T, the set ET of profile not eliminated by T is a compact subset. Recall that a profile is eliminated if there is a player I such that you have this inequality. Okay, so if there is no I such that there is this inequality, you have the inequality, large inequality in the other direction, and this gives you a set which is at the same time convex, okay, and compact by continuity. Okay, so now you want to prove that the intersection of this ET is non-empty, okay, and since these sets are compact, okay, it's enough to show that for any finite family, the intersection is not empty. Okay, so I now consider the case where for each player, his set of strategy is the convex whole of the TIK. TI is the strategy of player I that appears in one of the T in my finite family. Okay, And for each player, I take the convex hull of this set. Okay. And obviously, an equilibrium of the reduced game will be in the intersection of the ETK. Okay. So again, this proof is not constructive. Okay. And it shows that if there were no equilibria, there will already be a finite game, let's say, where without equilibrium. And now the proof is as follows. G is quasi-concave, so it implies that the best reply has convex value. This is standard. And now I'm using the continuity and compactness condition to show that the best reply correspondence is compact and convex value. Okay? And the joint continuity hypothesis implies that the graph is closed. Okay.
Just.
So, sorry. So for each player I, if I look at the best reply of player I to a profile of his opponent, this will define a compact and convex set. Now, to prove that the graph of the correspondence is closed, I use the joint continuity. Okay. This is the main difference with the zero-sum case. Okay. And now I use the fixed point theorem for correspondence, okay, defined on S, which is the product of SI. So I use Fan theorem, okay. I have closed correspondence with non-empty compact convex value on a compact convex set. So there is a fixed point, and as we saw at the very beginning, a fixed point of the best reply correspondence is an equilibrium. For part 2, if the set SI is compact, the set of Borel measure on SI also convex and compact for the weak star topology. And if GI is continuous, its extension, so the multilinear extension to the product of measure, okay, is also continuous. Okay, again, for the weak topology, you can use, for example, Stone-Weierstrass to approximate your function by product of function of one variable. Okay? And this is how to get the joint continuity. And then you use part 1 because you are in the case where the set are convex compact and the function is continuous and quasi-concave since it's multilinear. For more result on this proof, see Mertin Zamir 1.4 and the book with Rida Laraki and Jérôme Renaud, chapter 4. Okay, consider the finite case. In this case, finite game, so every player has finitely many strategies, okay, and the proofs are simpler and more precise. Okay, so the finite assumption allows for a more precise analysis. First, a mixed sigma is a mixed equilibria if and only if you have not a best reply, if you are not a best reply, then the weight is 0. Okay, it's just using the fact that you have a multilinear extension and a finite sum here. Okay, so it means that if you have a mixed equilibria, then the support of the strategy is included in the set of best reply. Okay, and there is also a simpler proof of equilibria, and this was the original proof of Nash in his PhD thesis. So every finite game has a mixed equilibria. And for this, he used the Nash map. Okay. Now, if you look at this, you will see that the Nash map is precisely the map that I used in the first proof by Brown and von Neumann using the differential equation. Okay, for if you look at the case, it's a positive part of the payoff, but the it was for an antisymmetric game, so it corresponds to this. Okay, so Joseph Hofbauer calls this dynamic Brown von Neumann Nash dynamics. So the map is as follows. You also say to a mixed strategy, So starting by the strategy sigma, you look for player one, his component is sigma I, and the weight he put on SI is sigma I of SI. So this is the weight that the player I put on the move SI. And then you compare the payoff of the move SI to the average. If SI is better than the average, you take it, and otherwise you put 0. Okay, so you take the positive part of the difference here, and you normalize. Okay, so F is well defined. Okay, clear, and everything is positive. Okay, and the sum is 1 because you have normalized. So you have a map from the simplex to itself. This map is clearly continuous because the payoff is multilinear here, and sigma is convex compact. So you use Brouwer fixed point theorem. You don't have to use Percutani. You don't have a correspondence here. You have an application that associated to a strategy. So let us prove that every fixed point is an equilibrium. Okay. If it's not an equilibrium, it means that there is some UI which gives more than sigma I. Okay. Then the sum over all possible deviation of the positive part is positive. Now, among the strategies that you use, there is one pure strategy that gives less than the average because G of sigma is the barycenter of this on this support. Now, for this SI, which gives less than the average, you have G of, so since you have a fixed point, sigma of SI is this. So it's sigma of SI plus the difference between SI and sigma I, but the positive part is 0. And you divide by this, and here you have one term which is strictly positive. So this is strictly less than sigma I of SI, but we assume that sigma I of SI is strictly positive, but here you have a contradiction. Okay, and it's clearly easy to see that if you have an equilibrium, then you have a fixed point, because for an equilibrium, these quantities are all 0. Okay, so you have 0 and you solve. Good. So this was the proof in Nash thesis using this map. Okay, and we'll see again this map in the future. So algebraic approach, I'm still in the finite case. We assume that each set of pure strategies is finite. I call it cardinal Mi. So again, now can be identified with a point in an Euclidean space. For example, if you have two players and each player has 2 strategies, a game is defined by 8 numbers that correspond to, once you define the order of strategy, it corresponds to this. Okay. So a game is a point in some Euclidean space, and the set of equilibria is defined by a finite family of polynomial inequality and large inequality. And the proof is clear. An equilibria is this. So this means that you have a point in a simplex. The sum for each player, it's a probability distribution. So sum is 1 and the components are positive. And the payoff, if you use sigma, which is the multilinear extension, so this is polynomial, gi of s is a constant, this parameter, is greater than what you do if you change to ti. Okay, and there is finitely many ti. Okay? So why do I have finitely many inequalities? Because it's enough by multilinearity to compare to extreme point, and there are only finitely many extreme points. Okay, so an equilibria is a solution of this finite set of inequalities where the unknown are the sigma I of Si. Okay, namely the optimal strategy of each player. Okay, so it's quite a nice set. However, you may have surprise. So the corollary, the set of equilibria is semi-algebraic, okay, finitely many polynomial, and it's a finite union of a close connected component. So I give 2 examples. One example is 2 players. So again, player 1 has 2 strategies, top, bottom. Player 2 has 3 strategies, left, middle, right. The first component is the payoff of player 1. The second is the component of player 2. And the set of equilibria in this game is defined as well. So the bottom line, top, bottom, correspond to the set of mixed strategy of player 1. It's a simplex in dimension 1. Okay, you have 2 strategies. And the triangle M LR, or left, middle, right, correspond to the simplex of mixed strategy of player 2. Okay, so the Toblerone bar correspond to the product, and the seek line correspond to the set of equilibria in this game. Okay, so you can check easily that you have all this line here, okay, which is piecewise linear connected. So there is one connected component, piecewise linear, is a set of equilibria in this game. Another example due to Kohlberg and Mertens is as follows. So you have now 2 players and 3 strategy for each player, left, middle, right, top, middle, bottom, first component, payoff. Okay, and there is one connected component of equilibria, which is of the form, so you go from top left here, so on the left top corner, okay, with payoff 1, 1, and then you keeping top, all these are equilibria, okay, and then you have all this mixed strategy here corresponding to top right up to middle right, and all this in the middle, and then it goes down to BM, it goes to BL, and goes there, okay. So this is the this line between TL and TR correspond to the mixed strategy between top left and top right. Okay, it goes above M. Okay, this is the line going from, so this corresponds to mixture where player 1 plays top and player 2 is playing a mixed strategy with support left right. Here player 2 is playing right and player 1 is playing a mixture of top and middle and so on. Okay, so this is homomorphic to a circle. Why is this interesting? It's because of the Euler index of the circle is 1, okay? And this implies that this component cannot be an attractor for a dynamic. Okay, and showing that there are interesting property for the set of equilibria. I will come back on this later if you have questions. In addition, this is robust, meaning that you cannot drop any part of this component. If you choose any of these equilibria, then there will be a nearby game having only a single equilibrium, which is precisely near the point you choose. Okay. So, for example, if you take this equilibria in the previous game, then it will be the only equilibria of this game. Okay, which is a perturbation of the previous game. Okay. So it means that all these points here in this game are basically essential. Okay, you cannot drop any of them. Okay, and you have to keep all the circle. Okay, so now let's speak about equilibrium and variational inequalities. So for various class of games, you can express equilibria as solution of variational inequalities. It's not always true. I will discuss because the property for Nash equilibria is that the payoff has to be quasi-concave. Okay, and here we will ask for more. So the example are finite games. In finite games, you can define the vector payoff function by looking only at the payoff induced by the move of the strategy of your opponent and indexed by your own moves. Okay, so given the strategy of your opponent, you look at the vector if you play your first strategy, second strategy, and so on. So this is called the vector payoff function for player 1, Vg of I. Okay. And the U component of Vg of I is the payoff if you play strategy U, given the mixed strategy of your opponent. So since everything is bilinear, is multilinear, the payoff is a scalar product of the vector payoff and your own strategy, and you have a Nash equilibria if and only if you have this variational inequality. If you have a concave game, so let's say you are in a Hilbert space, and you assume that the payoff function is concave and C1, okay, then you have a Nash equilibria if and only if when you take the gradient of the payoff of player 1 of player I with respect to the I component, you have this inequality, okay? Because you are just looking at deviation with respect to the I component and the function is concave. Okay? The last example will be population gain. So this is a definition. You have a finite set of population of non-atomic players. Okay? And for every point I in capital I, Si is a finite set of action of population I. And Xi is a simplex over Si. Okay? Now the interpretation of a point in a simplex is not a mixed strategy, is the proportion of players in population I that play a simple OOMP. So Xi is the proportion of players in the population I that use the move U. Okay? And you have finitely many population. You have a function ki that goes from x, which is the product of the xi, the product of the simplex, and goes to r to the power si, where kiux, it's a payoff of a member of population I that is using the action u given the configuration x. Okay? So the configuration describe the behavior in the population. Okay, and so to give you an example, you may have a population of foxes and a population of rabbit, and you have in the population of rabbit a proportion of blue and red rabbit, and in the foxes you have a proportion of large, small, and a big, middle, and small foxes. Okay, and KIU will be the probability of survival of a small rabbit. Okay, given the proportion of small and large rabbit and small, middle, and large foxes. Okay. So an equilibrium, which this definition is due to Vardrop, 62, says the following. If there are in the population I people using the move U, it means that they cannot do better. Namely, the payoff, if they use U, is better than any payoff they could use by using V. Okay, so this is true for every choice in the population I and for every population. Okay, so K is the payoff, and you have this this way of writing the previous inequality. Okay, because on the support you have inequality, so it means that you have this. Okay, so this is the way of writing the equilibrium in this framework. Okay. So you see that a typical example of this will be a congestion game. I correspond to the type of the agent and U to the link in the network. Okay. So just to compare this population game to strategy game, let us look at the Pigus example. Okay, you have two roads, top and bottom, that link the origin O to the destination D. On the top link, if the conjecture, so there is only one population, is the cost is X if the conjecture in X. Okay, and on the bottom there is a constant cost one. Okay, and we have two population, and each of the population has a size 1/2. Okay, so the agent in each of the population of size 1/2 can choose to go top or bottom. Okay, but they are non-atomic, so they will not change the proportion here and not change the cost. Okay, so there is only one equilibrium, because if the total amount of people in top is strictly less than 1, then all the agents will go there because they will get less than 1. So the only equilibrium is where all the agents go top and the cost is 1. Okay, so the only equilibrium is S1, S2 is 1, 1, where Si is the probability or the proportion of taking top in the population I, where population is either 1 or 2. Okay, so the cost is 1. So I consider now the same game, but rather than having two populations, I have two players. Each player has a size, which is 1/2, okay? And choose to go top or bottom. But there will be two games. In the first case, you have two players that control each a mass 1/2. Okay, so they can split the mass and send part of the mass top or bottom. Okay, and it's easy to see that in this framework, there is only one equilibria where the player will send 2/3 of their mass top and 1/3 bottom, and their mass is 1/2. Okay. The other case is when this mass is not splittable. So what they can decide is to the probability according to which they will go top or bottom. Okay. If you think in terms of network, then you want to send a large packet through a network. In the first case, you can split your package into small package. In the second case, you have a big file and you cannot split it. So you have to choose a network and you will choose it at random. Okay. So in this case, if it's not splitted, the player use mixed strategy, and the set of equilibria is of the form one player plays top and the other is playing a mixed strategy. So you see that the equilibria in this game, in the Pigou games, are of the form. If it's an atomic, 1/2, it's a population game, the only equilibrium is 1/1. If it's a two-player splittable, the only equilibrium is 2/3, 2/3, and it's two-player non-splittable, the set of equilibria is this line going from 0/1 to 1/1 and 1/0. Finally, if there is a dictator or a planner who decide for the people, then they will say half of the people should go top and half of the people should go bottom, and this corresponds to the social optimum. Good. So now let us go to the general case of variational inequality. I consider a finite collection of convex compact sets, Xi, let's say in Hilbert, and I define evaluation mapping, okay, going from X to, so X is a product going to Hi. So each phi I is defined on the product, okay? You don't have a collection of function defined from Xi to itself. You have function defined on the product with value in the Hilbert space. And I will say that the Nash equilibria of these evaluation mappings, okay, is a set of X satisfying this, phi of X, X1, okay? Where phi of X is the sum over H. Okay? So all set of previous set of equilibria can be written this way, but the function phi will vary. In the first case, phi is the vector of payoff function. For concave game, phi is a gradient of the payoff of player I with respect to his own variable component, okay? And in case of population game, phi is the payoff itself, okay? So all this game can be written as with evaluation mappings, and let us look at this stuff. So the set of Nash equilibria is given by this. Okay. Recall that pi c denotes the projection to the closed convex set. Okay, and consider the map T from the product of Xi to itself, defined by you take X, you add phi, and you project again. Okay, so a set of Nash equilibria is a set of fixed point of T. It's just a characterization of the projection. Okay, if you look at the projection, you look at X plus phi minus the projection, scalar Y minus the projection. This is less than 0. This is the definition of the projection on a convex set. Okay. Then you see that, and there is only one point, but if you have a fixed point, then it will be a solution of this. Okay, because if you put here X, you have X plus phi minus X, so you have phi, Y minus X, and this is the definition of Nash equilibria here. Okay, so the set of Nash equilibria are precisely the fixed point of this operator. In particular, this shows that if the evaluation map are continuous, then the set of Nash equilibria is non-empty because it corresponds to the fixed point of this set. Okay, so this is proof of equilibria for C1 concave game, okay, which is hypotheses that are much stronger than the Nash result. An alternative characterization is not the projection on C, but the projection on the tangent cone to C, okay? So is this G should be phi, okay? And it's just due to the fact that if you take the limit of this, okay, so you project you take X, you go in the direction of Y, you subtract X and you normalize and take the limit, then you have the projection on the tangent space, okay? So this is equivalent to the previous. So these results are quite standard in the framework of theory of variation inequalities. Okay? So these are a few references, and these operators were used in operational research. Okay, so this, for example, Dafermos, Dupuis, Lagournet. There are plenty of references here. Now I look at specific classes. Okay, so first class will be supermodular games. Here I just want to describe a class of game where we don't use the usual fixed point theorem, neither Kakutani or Brouwer. Okay, it's a case where you have a lattice structure. So you look at the partial order on Rn, and you say that a subset is a lattice if for every 2 points in S, the supremum and the infimum is in S. Okay? And then you have a fixed point in this framework, which is Tarski, which says that if you have a non-empty compact lattice and F is increasing, then it has a fixed point. So think of increasing function from 0, 1 to 0, 1, okay? No continuity requirement, it's simply increasing, then it has to cross the diagonal. Because at the beginning, it has to be above 0. Okay, if f of 0 is 0, you have the fixed point, so you start above 0. And then you have to reach a point below f of 1, because f of 1 is below 1. Okay. Now the point is that your function is increasing. Okay, so when you are above the diagonal, okay, you move, and then at some point you will be very close to the diagonal, but then you cannot jump down. Okay, so you have to cross the diagonal, and this is Tarski fixed point. Now consider a strategy game where for each player you have a non-empty compact subset of Rm, and GI is upper semi-continuous, and the game is supermodular, saying that every SI is a lattice. GIS increasing differences. It means that if the strategy of the opponent is fixed, then when you move your strategy, okay, it's better for you if S minus the behavior of your opponent is greater. Okay, so it's better for you if you are facing somebody which is better here. SI is greater. And G is supermodular, meaning that you have this property. Okay, so you fix the strategy of your opponent and you compare two strategies SI and S prime by looking here at the mean and the max. Okay, so these are a natural property in a lot of models in, for example, industrial organization. And the result is like this, Topkins. Under the previous hypothesis, so the gear is supermodular, you have an equilibrium. Nash equilibrium. And the proof is basically that you look at the best reply, and the best reply will satisfy the property of Tarski theorem when you look at the maximum element of the best reply map. Okay, so you first show that the best reply map has maximal element, okay, and then you apply Tarski to the best reply. Okay, that's just to show that there are other fixed points than the fixed point using topological property. Okay, so this is a place where you use the ordered structure. Okay, now potential games. So potential games were introduced in the finite case. Finite case means that finitely many players, finitely many strategy for the player and mixed extension. And it was done by Monderer and Chaplet 66. A real function is a potential for the finite game if when player I is moving from SI to TI, it's like P. Okay, so the change in the payoff of player one when he's changing the strategy can be represented by the function P. for each I. Okay, so P represents the variation of P in the I component is the variation of the payoff of player I. In the first component, it corresponds to the variation of the payoff of player 1. Okay, so it means that to check equilibria, rather than checking on G, I, you can check it on P. Okay, because equilibria means that you look at the variation of the payoff of player 1, I, when he's changing his move. So it's enough to look at P. Okay? So equilibrium property can be written in terms of the potential. Okay? In particular, if you have evaluation function, then remember that the evaluation function were corresponding to the gradient. Okay, so here we said that a real function W, okay, is a potential for the game with evaluation phi if basically phi is equal to the gradient of W. Well, you can be a bit more sophisticated. It does not necessarily, it's not necessarily equals to the gradient, but it's proportional with where mu I is strictly positive, and this has to be true only on the tangent space. Okay, so this is what 11 says, that basically phi I is the gradient, except that you can. Okay, and what is the use of this? It's as follows. Take a game gamma of phi, so phi is the evaluation. Okay, so when you have a game, the evaluation is the function that appears when you write the equilibria as variational inequalities. And you assume that this game has a potential, then every local maximum of the potential is an equilibrium. And if the potential is concave, then any equilibrium of the game is a global maximum. And this is clear because the local maximum is this, okay? In particular, it applies this. Okay, this is the gradient with respect to I. And remember that the gradient with respect to I is here equal to this. This is strictly positive. Okay, so in terms of inequalities, you keep the property. Okay, so this is the use of potential for potential games. And we'll discuss a lot of this property this afternoon and next week. Just a nice example of a potential game, and that will be also useful in terms of stability of equilibrium. So you look at the minority game. It's a very simple game. You have 3 players, and each of the players has to choose one of 2 rooms. And you have one if you are alone in a room. Okay, and 0 otherwise. So there are pure equilibria of the form 1 player in a room and the 2 other in the other room. 3 players in the same room is not an equilibria because 1 player will go by himself in a room and will be alone, he will get 1. And mixed equilibria of the form you have 1 player in a room, the other in the other room, and the 3rd player can choose whatever he does, he will not be alone, so he will get 0. In addition, there is a symmetric equilibria where each player chooses to be in a room with probability 1/2. So you are facing 2 guys that will be in room A and B with probability 1/2. So you are indifferent and you can as well go to each of the room with probability 1/2. So the set of equilibria is homeomorphic to a circle. So this is like Kohlberg-Mertens example, but there is, in addition, an isolated point corresponding to the symmetric mixed equilibria. So this is the configuration. This is the set of equilibria, which is homeomorphic to a circle, and this is the completely mixed equilibria in the middle. Okay? And this is the potential game, and the potential is very simple. The potential is 1 if there is 1 player alone and 0 otherwise. So the potential is just checking whether it's Pareto efficient or not. Okay. So it's a very nice and simple game. Okay. And we'll use it to prove the stability of some dynamics. Dissipative game. We said that a game is dissipative if the evaluation function is dissipative. Dissipative means that you have this inequality. Phi of x minus phi of y, x minus 1 is negative. Okay, so minus phi, if you think of is monotone in the sense of Okay, in particular, the gradient of a C1 function is monotonic. Okay, so dissipative will correspond to gradient of concave function. Okay, in games we are maximizing, so we use concave function and the gradient will be dissipative. In optimization, people use convex function and the gradient is monotonic. So this notion of dissipative appears for strategy game is Rosen in 65 already. And in the framework of population game, Hofbauer and Sandon use the terminology stable games, but we prefer with Cheng Wang to use the notion of dissipative. Basic example of dissipative game will be 2% zero-sum game. Okay, so assume this was proved by Rockefeller. You assume that you have a function f from x1 cross x2 to r, which is C1 and concave convex. So x1, x2 are compact convex, and your function is C1 in each variable and concave convex. Then phi, which is the gradient of f with respect to the first component and minus the gradient with respect to the second component, is dissipative. Okay? And this corresponds to the phi of the game. You remember, phi is the gradient of the payoff. But in a zero-sum game, the payoff of player 2 is minus f. Okay? And the proof is very simple. You use here, you change from yi to xi and use the function, you use the fact that the function is concave. Okay? Now you change from xy to x1 as well. Okay? And here you use the fact that the function is convex. Okay? So minus f is concave. Okay? And you change here the inequality, you sum so that you get this property, and which is exactly this inequality. Okay, so the basic example of dissipative game are zero-sum games. I define now another set, SE. So NE, think of Nash equilibria, okay, was the set, I remember, I just go back to the definition, is a set of x satisfying phi of x minus y is positive. SE, I put y here, okay? So SE is a set of x that satisfies phi of y, x minus y is positive for all y, okay? It's always the case where x is compact convex. Note now that this is an intersection of L space, so this set is always convex. Then there are two properties due to min t. First one is, assume that phi is dissipative and x is convex compact, then this set SE of phi is non-empty. Okay, and the proof is as follows. I look at the y, I fix y, and I look at the x satisfying this for this specific y. Now SE of phi is the set, is the intersection over all SI. Okay, because the point is in this set if this is true forever. Okay. Now this is the convex set. X is compact. Okay. This is closed. Okay. So this any SI will be compact. Okay. So to prove that the intersection is non-empty, it's enough to prove that for any finite collection, there exists X satisfying this. In fact, I will even prove more. I will prove that for every finite collection yi, there exists X in the convex hull of the yi satisfying this. Okay, so this will prove the property that SI of phi, SE of phi is non-empty. And what is nice is the proof is using the min-max theorem. Consider the finite 2% zero-sum game defined by the matrix. So Aij will be phi of Ayj yi minus yj. Okay, you have finitely many points, y. Okay, so this matrix is it's well defined. Now I decompose A between the symmetric and antisymmetric part. So A is B plus C. B is the symmetric part of A, and C is the antisymmetric part. The crucial point is that B has no negative coefficient. In fact, look at Bij, so you multiply by 2, it's Aij plus Aji. So Aij is this, Aji is the second term, and this is exactly this the fact that phi is dissipative. Okay, so the matrix B has positive component. Now the matrix C is antisymmetric, so its value is 0. Take an optimal strategy of player 1 in the game C. Then you look at what it gives in the game A. It gives the payoff in B plus the payoff in C. In the payoff in C is positive, and the payoff in B is positive because B has positive coefficient. So this implies that you apply to A is positive against every J. This gives, remember the definition of A, this gives this. Okay? Yes? Now you put the UI inside. Okay? So you let X to be the convex combination. So remember, U is in the simplex. Okay? So it's a convex combination of point in I. So this is a convex combination of the YI. So it's a point in the convex hull. And it simply says that the previous inequality I was looking for, phi of yj, x phi of yi, x minus yi is positive for every y. Okay. And that's it. So this is the proof of mean t. So what I have here is that this set SE of phi, it's convex. It may be empty in general. Okay? So there is no general property like Nash equilibria. Okay? It's not. But if the game is dissipative, it's non-empty, and the proof is elementary, meaning that it relies on the min-max theorem on the separation, while it's not true for Nash equilibria in general. It uses a fixed point. Okay? And the proposition due to min t again is that if phi is dissipative and continuous, then both sets coincide. In one direction, you don't use continuity. If phi is dissipative and you have an equilibria, then phi y minus phi x, x minus y is positive. You remember, you change the sign. So phi yi is greater than this, and this is positive because you have an equilibrium. In the other direction, assume that phi is continuous. Okay, so you start with a point in SE, z in x, and you look at y of the form x plus t z minus y. Okay. Since you are in the set SE, you have phi of y, x minus y positive. But x minus y is t x minus z, because you change the sign here, and y is there. Okay, so you have this inequality. You can drop t, which is positive, and then you let t here goes to 0, and you use continuity of phi to get phi of x, x minus z positive. This is true for every z. So you are in Nash equilibrium. Okay, so that's it. And this is the end of what I wanted to say this morning. Okay, so when you look, so there is a subset of games for which you can express Nash equilibria through variational inequalities. Okay. It contains population games, it contains finite games, and it contains C1 games where the function is concave with respect to the payoff of player I is concave with respect to his own component. Okay. For this class of games, you can express Nash equilibria as variational inequalities, and there are subclass of this evaluation function that are very important in terms of application. Two classes are potential games and dissipative games. These classes will play a crucial role in next week when we'll speak about no regret procedure in learning and convex optimization. Okay. And here are the reference. So Aubin-Celina differential inclusion, this is needed for the best reply dynamics. You remember that there was a differential inclusion and there was a different dynamical system with this differential inclusion. So the existence and the property will be in the paper by Aubin, in the book by Aubin-Celina. Homan-Machler, this was the min-max example. Berge, this was the intersection lemma. Blackwell, this was the unilateral procedure and the C sequence. Okay, I use Bonance for the envelope lemma, fixed point of Brouwer. Then you have Brown, Dafermos and the Dupuy were variational inequality. Fakinei and Pan, it's also variational. Fixed point of Fan. Gale was this example symmetrization of the game. Gilboa Matsui, this is the best reply dynamics. Gilberg is a fixed point. This was a continuous time. This of Bauer was also mid-max. Of Bauer standard stable game. And Kakutani, okay. Kinderlehrer variational, the example of Mertens, and the proof of Loomis, our book with Jean-François, the proof of Minty, Monderer and Seller was to prove the payoff for fictitious play, the average payoff. Monderer, Chapley, it's potential gain. Lagournet, it's the application of variational inequality in operational research. Nash, equilibrium point. Rivière was the payoff. And this is Robinson, Rockefeller for the property of dissipative for zero-sum game. Rosen was dissipative game. Sandholm potential, the example of Shapley, Sion minimax theorem. And Tersky and Taylor and Jonker was the replicator dynamics. Tompkins was for the proof using Tarski. This is Ville with the first min-max theorem using the Ann-Banach. This is the initial von Neumann theorem. Wardrop is Wardrop equilibria, and Weil is for the min-max theorem in ordered field. That's it for this morning. Thank you very much.